What does an earthquake forecast tell us? Well, in this example, it indicates in yellow which regions are at greater risk of severe ground shaking. Forecasts like this are important. For instance, they will have influenced the design of this building and our chances of walking back out. The more observations we have of past earthquakes, the better our forecasts can be. But in New Zealand, this is tricky. We are a young nation and our earthquake records are short. We can extend these records by dating damage features like these, but from ancient earthquakes. But erosion complicates things and, wipes out these features, erases them from the record within a few thousand years. What if we look below the surface, away from erosion, like in caves? It turns out caves preserve evidence of earthquakes, and not only for a few millennia, but for tens of thousands of years. I've been working on this with the research team, cave research team, and what we've found is that the best evidence of earthquakes in caves is actually hidden in the chemistry of these formations. How does it get there? Well, when the rock above a cave gets fractured during an earthquake, it releases extra magnesium into the groundwater, which seeps into the caves as drips. Now, in the caves there are also stalagmites, like this, which grow upwards, layer by layer, using minerals from the drip water. So when the drip water has more magnesium than usual, it forms a magnesium-rich layer in the stalagmite. Imagine if we could slice open a stalagmite like this, measure its chemistry from top to bottom, and produce a record of major earthquakes based on its magnesium. Well, we tested this idea on this stalagmite from near the Alpine Fault with some promising results. Not only does it contain evidence of earthquakes, contains evidence of major earthquakes that correlate with known Alpine Fault events. Not only does it do that, but this stalagmite record extends much further and contains evidence of earthquakes as yet unknown to science. So, to summarize, let's put on our helmets and break down the wall of earthquake forecasting. Thanks.
Kia ora, Jeff. Any questions for Jeff?
Sounds like a novel approach and really interesting. Would you need a network of these sort of cave systems throughout New Zealand that you'd be able to utilise, you'd have to utilise to localise where the events occurred?
Yes. No, that's a very good point. So that's the stretch goal is to reproduce this kind of study at multiple caves around New Zealand, and then correlate events in each record. Well, it's really like regions like the Hikurangi subduction margin, which are high seismic hazard in New Zealand, but poorly understood in terms of the earthquake record. This would be a way of detecting in the past when there's been potentially extensive subduction earthquakes, because we'd expect to see events in multiple cave records that happen at the same time over a large area. So that's a good point.
Just a quick follow-up. The magnesium, can it be something else that would cause it? You say that it matches the known earthquake record so far, but can you exclude that it's not coming from something else?
That's a very good question. So, there are other processes that can generate more magnesium. So we're looking at magnesium to calcium ratio in particular, and there are other processes related to climate that can do that. But the magnitude of increase that we expect from this mechanism is up to 10 times the normal magnesium to calcium ratio in the stalagmite. And on top of that, we have other tools in the stalagmite, like isotope or other elements, and then magnesium and calcium isotopes, potentially to tease apart the different processes that could be affecting this magnesium enrichment.